So I'd like you to meet Aaron Pancost, one of our TAs. He had some questions about the last video. So shoot, Aaron, what wasn't clear?
So how come you just got rid of these terms here to get that the variance is this term? Don't you have to subtract the square of the expected value?
That's right. Variances are supposed to have the means out, aren't they? Yes. This is one of the very interesting properties of continuous time models. Let's do it a little bit more slowly. Let's do what you want to do. You want to take dxt. Let's look at dxt squared. Let's just square dxt mechanically. What do you get? You get mu squared dt squared. You get sigma squared dz squared is dt, right? That's the key. That's the key. I said we were going to use that. dc squared is dt. So that's that term. And then a cross term. Now let's look at the sizes of these terms. That's of order dt. Calculus says keep things of order dt. That is of order dt to the 3/2. We have dt times the square root of dt, and that's of order dt squared. As the time interval shrinks, those things go away. So all that's left is dx squared equals dt. That's just amazing. This thing looks like a random variable, but in fact, it's of order dt. It's non-stochastic. So the variance of dx squared is just sigma squared dt. What's going on here is that the randomness of a diffusion at small time intervals is so much bigger than the mean that it's the same whether you take the mean out or not. Cool stuff, eh? To review, though, there's a rule in how you do these manipulations. You expand things just like you do in calculus. You keep things of order dz, dz squared equals dt, and you throw out stuff of higher orders, just as you did in calculus, but you got those root dz terms. OK, what's next?
So back here, when you define the random walk as a sum of discrete time processes, it's linear in the variance and not the standard deviation.
That is terribly key. The key is that that's what drives the whole, why are we getting this square root of dt business? It's because we have the variance is linear in the time interval, not the standard deviation linear in the time interval. But of course, that follows just from the definition. Let's take the variance of that guy. The variance of that guy is the sum of the variances of the individual terms.
Which is a property of normal distributions, right? Not necessarily of another distribution.
No, it's a property. The variance of the sum, let's take the variance of all that, is the sum of the variances.
No matter what the distribution.
No matter what the distribution.
Because it's IID.
Okay? And then the covariance terms all disappear because it's IID. So that's equal to the variance of the sum is equal to the sum of the variances of epsilon t minus j. There's j of those. So variance scales with time. Standard deviation scales with square root of time. That's what it looks like. And that's what's at the root of all our square root of dt and all the other interesting properties here. Next.
So what is going on with this?
The general form of the diffusion.
Right.
Yes.
How does that map into the diffusions we've already looked at? What are we doing?
So for example, this diffusion just has constant coefficients, whereas this diffusion allows the coefficients to be functions of state variables, x itself, functions of time, or functions of other variables that are going on. That's how you build great generality into it. For example, here's a diffusion, a more general diffusion. The mu term allows you to control the drift. Where on average do you think things are going to go? And in a different state of the world, the drift might be pointing in a different direction if x were different. The sigma allows you to control the volatility depending on other things that are going on. A good example that's just a little more general than that, but not so confusing as that, this thing here really should be written as dpt equals mu pt dt plus sigma pt dzt. And now you can see that the drift term contains the variable itself. I like to write it that way because that's a rate of return. But really, if you're going to do things right, you write it that way. This is the formula for many more general processes. One of the biggest things we like to do in finance, we know that volatilities vary over time. So one big stochastic volatility processes might let that thing be equal to like sigma square root of xt dzt. And then if x is higher or lower, it gets more or less volatile. All sorts of fun things you can do with that set of ingredients. Thank you.